Hello guys and welcome to another calculus video. In this video we're going to be solving this nice little integral that was recently posted in my Discord server, so thank you Elmo for posting this problem. I'm going to go ahead and solve it really quick. It's not too complicated of a problem, but it has some standard methods, but I still think it's a pretty fun problem, so let's go ahead and jump right into it. So we're going to be using a few functions here. We're going to be using the digamma function. We're going to be using the Euler reflection formula for the gamma function pictured right here, and this lemma from a previous video right here of this summation right here. I'll go ahead and link right here the video in which I actually proved this lemma right here. So if you guys want to go check that out and verify it, please be my guest. So let's go ahead and jump right into the problem. So first thing we want to do is definitely rewrite this in a better way, because the cosx on the bottom just makes everything look very nasty. So we have cosine of x over x hyperbolic cotangent of x dx is the same as cosine of x times sine hx over x cos x dx. Now notice that this sine hx over x sort of cancels, they sort of cancel with each other at 0, and that's the only reason that this integral actually converges. So let's see if we can find a way that we can sort of compact these two functions into one. So the way I'm actually going to do this is I'm going to rewrite sine hx using the exponential form, 1 over 2x times e to the x minus e to the negative x, which is the same as 1 over 2x times e to the alpha x evaluated at alpha equals 1 and alpha equals negative 1. And this is the same as 1 half times the integral from negative 1 to 1 of e to the alpha x d alpha. So we can go ahead and substitute this in the integral from 0 to infinity of cosine of x over cos of x times 1 half the integral from negative 1 to 1 of e to the alpha x d alpha dx. Then we apply Fubini's theorem. Absolute convergence here is totally cool, as long as we use the limit as alpha goes to 1. We need to be wary of that. So this is really a limit right here. And so we end up with 1 half the integral from negative 1 to 1 of the integral from 0 to infinity of e to the alpha x cosine of x over cos x dx. Now let's go ahead and evaluate the inner integral here. So e to the alpha x cosine of x over cos x, essentially what we're going to try to do here is everything here is in nice exponential form, so let's try and make this into a summation of exponents, of exponential functions, sorry. So we have e to the alpha plus ix plus e to the alpha minus ix. This should all be... Oh no, sorry. Yeah, so I wrote everything in exponential form here, so that means cosine of x is e to the ix plus e to the negative ix over 2, and that cancels with the 2 from the cos x. So we have these exponents on the top and these exponents on the bottom. Then we're going to multiply by e to the negative x on the top and bottom, so we get this shifted exponential here and this shifted exponential here as well. And then we are going to get 1 plus e to the negative 2x dx, right? Then we're going to use this 1 over 1 plus u equals the sum from n equals 0 to infinity of negative u to the n power. And so we can expand this as an infinite series and get rid of the exponentials on the bottom. So overall, we'll end up with a sum from n equals 0 to infinity of negative 1 to the n times the integral from 0 to infinity of e to the negative 2n plus 1 minus alpha minus I x plus e to the negative 2n plus 1 minus alpha plus I x. And so overall, when we evaluate both these integrals, you can do using u substitution, or the Laplace transform just becomes 1 over 2n plus 1 minus alpha minus I, and 2n plus 1 minus alpha plus I. Then this is just a simple application of the formula that I showed you at the beginning. In this case, a equals 1 minus alpha minus I, and b equals 2. In this case, a equals 1 minus alpha plus I, and b equals 2. So we end up with negative 1/4 digamma. I'm actually not going to say all this. It's just a bunch of digamma functions right here. As you can see, we just went ahead and plugged in these formulas exactly. Now all we have to do is integrate them from negative 1 to 1 with respect to a. Also, I multiplied by 1 half because I missed that from earlier. So in order to integrate these, the main thing to remember is that the digamma function is the derivative of the natural log of the gamma function. So integrating this will just give us the gamma function. Also, this 1/4 here is actually not something we have to worry about because we have negative alpha over 4. So when we integrate using the chain rule, this is just going to disappear, and also all the signs will flip because alpha is negative inside of the digamma function here. So all of these line up with terms of the natural log, and notice I combine them all into one natural log because of the properties of the natural logarithm, I can go ahead and do that. So, from the first one, we get ln gamma of negative I over 4 over 1 half minus I over 4. Again, just plugging in negative 1 and 1 into this and putting it in ln gamma. Then we also get gamma of 1 minus I over 4 over gamma 1 half minus I over 4. From this term, we get gamma of I over 4 over gamma 1 half plus I over 4. And from this term right here, we get gamma of 1 plus I over 4 over gamma 1 half plus I over 4. So, we just go ahead and pair up all of these gamma functions in a very specific way. So, we want to apply this formula, gamma of x times gamma of 1 minus x equals pi cosecant of pi x. So, we're going to pair up all the terms which are x and 1 minus x. So, that's going to be this term right here with this term over here, this term right here with this term over here, this term, and then this term and this term. And when we go ahead and do that, we get a lot of pi cosecant pi x's. So we get 1 half natural log of pi cosecant negative pi I over 4 times pi cosecant pi over 4 pi over pi squared cosecant squared of pi over 2 minus pi over 4. Now we're going to apply a bunch of identities right here. First of all, cosecant of ix equals negative I times cosec of x. Then we get cosecant of pi over 2 minus x equals secant of x, and secant of ix equals sec of x. So on the bottom here, we're going to get secant squared of pi I over 4, which is just sec squared of pi over 4, right? And on the top here, this negative sign is going to come out, and then we're going to get two negative I terms multiplied together, which negative I times negative I is just negative 1, and then it's going to cancel with that negative sign. So we're just going to get cosec squared of pi over 4. And this is what we end up getting, 1 half natural log of cosec squared of pi over 4 over sec squared of pi over 4. We can cancel out these squared powers right here with the 1 half due to the properties of the natural logarithm, and we just get natural log of cosec of pi over 4 over sec of pi over 4, which is the same as cosine pi over 4, or cos pi over 4 over sin pi over 4, or natural log of hyperbolic cotangent of pi over 4. So that was a pretty straightforward problem. But anyway, I hope you guys liked the video. And if you want to see more problems like this, please go ahead and let me know, or go ahead and leave suggestions in the comments, or you can go ahead and join my Discord server and add suggestions there. Thanks so much for watching. I hope you enjoyed the video, and I'll see you next time.